So a two-way table looks like this. Okay. We did not talk about these things, but these are where we total them up. This is called um brain. Yeah, that's right. This is called marginal distributions. And I can add, I believe. The proportion thing would not really be part of this marginal, but you could put the proportion in each one or things, and we'll look at different tables that have those. Okay. But this thing in the bottom corner is called a table total. Useful pieces of information. So the marginal, they're called, marginal distribution. Conditional would be putting in percentages of each one, like 24. Oh, wait, no. I guess this is kind of weird. This isn't the greatest two-way table for this. There's a better one later because it's saying there's um but here is the different graphs of the treatments. There are two treatments, disipramine, lithium, and then they use the placebo to treat 24 cocaine addicts trying to quit. So the population for this is people trying to quit their cocaine addiction. We're not particularly interested in how many people quit that aren't trying to quit, because the answer is usually about zero. Yeah. Like if you don't want to quit, you probably aren't. So that's not necessarily a population we'd be interested in studying. So what we're interested in comparing is if the success rates are different. Okay. So disipramine is an antidepressant drug. This is my two-way table. So we had 24 in each. We split it then into relapse or not relapse, or yes, no. So my marginals here would be 10, 28, 48, 24. And if you add them up, you get 72 either way. That's an important thing. Okay. You guys remember having an expected count, right? Okay, so my 3x2 table. You're going to calculate chi-square essentially the same way you did, which was chi-squared was O minus E squared over E, correct? I think. Yeah, and then you add them all up. So calculating the expected count, though, this is where your totals become really important. Expected count becomes row table total times column total divided by table total. That becomes important information to know in case you have to do it by hand, or if they ask you what is the expected count. That feels most likely. Most of these you can just run on the calculator, but they might ask you, what is the expected count for this? And that's where you're going to have to know. Row total times column total divided by table total. So if we calculate our expected counts, free throws. We'll skip over this for now. So here is our table, and we'll put our totals back in. So 24 times 24 over 72 equals 8. That goes there. Now, because all the rows were 24 and this column is 24, all of those are going to be 8. The next one, 24 times column total 48 over 72 is 16. Again, since every row was 24, that whole column's going to be 16.
What is that?
10 plus 18 plus 20 is 48. So I'm adding, and yes, these better add up to the same. Your expected should add up to your same totals. If that makes sense. If they don't add up to the same total, we've got some issues going on here. So that gets me my expected counts. My degrees of freedom. So number of rows minus 1 times number of columns minus 1. Okay, and what are we testing? With chi-square, is there any association or is it independent, essentially? Do you get what's expected? Is what you're testing. Okay. What is the difference with this and goodness of fit? Goodness of fit was a bunch of things with one column. This has multiple columns. Okay. So again, we add up this. So looking for my cocaine addiction one, looking at it, 14 minus 8 over 8, 36 over 8, 4.5. Observed, there were 14 that didn't relapse from decepramine.
Oh, okay.
So if I'm looking at this, where am I? If I'm looking at this is my observed table. I have to do this for every one of them. 14 minus 8 squared over 8 plus 10 minus 16 squared over 16 plus 6 minus 8 squared over 8 plus 18 minus 16 squared over 16, etc. That makes sense? So that's calculating it. I do not think you'll have to show the calculations, but it would not surprise me at all if you have to show an expected value if chi-squared is on your exam. So completing the whole chi-square test. Identify the population of interest, state the hypothesis. So H naught P1 equals P2 equals P3. The proportion of cocaine addicts who avoid relapse are all the same is your H naught. Basically, all of these, none of these treatments are any different. AHA, not all three proportions are equal. What? Yes. So you could say P1 is not equal to P2 is not equal to P3, but the reality is if one of those three is different. So P2 and P3 can be equal, but P1 being different will give you a chi-square that where you reject. So anywhere it's not completely true for HA. Okay, well, and we'll talk about testing where your difference is if you get a difference. So your assumptions. The data comes from independent SRSs from the population of interest. They randomized who was in which group, so we're going to treat it as SRSs. All selected cell counts are greater than 1 and no more than 20% are less than 5. And we're looking at the expected counts, not the actuals. The expecteds were all 8 and 16. So none less than 1 and no more than 20% less than 5 are your two conditions. Okay? So you can't expect any of them to have less than 1, period. You need enough data that you expect to have it. And if you're in this one out of 6, you can have only one that's less than 5. Because we had 6 cells in a 3x2. We're going to do some 3x3s. So that would still only be 1 cell that can be less than, because that's 9 expected. But if you did a 3x4, you could have 2 less than 5. 20% at 12 is about 2. It's a little more than 2. That makes sense? So those are my conditions. Carry out the procedure. You add them all up. You get a chi-square of 10.5 and a degrees of freedom of 2. You could look that up in the chi-square table. Degrees of freedom 2. 10.5 is somewhere between 0.01 and 0.05. So we're pretty sure we're rejecting. There is a difference here. One of them is not the same. I think we can look at it and go, that one is the separate mean. You'd need to run a second stats test to compare, but. So doing it on a calculator. You have to enter it as a matrix. So you make a 3x2 matrix. You enter your data. I'm going to store this matrix as A. And menu, statistics, stats tests. And this is a chi-square two-way test. This is the one you use most of the time. Observed matrix. I called it A. This is why you need to name it. You don't need to calculate any of the other things. It calculates your observed for you, gives you your degrees of freedom. Okay. P-value of 0.05 or 0.005. So we're rejecting and concluding HA that there is a difference. Any questions on this piece? This isn't so bad, is it? The Here's printed, here's stats printouts and things. So follow-up analysis, what we do is we do a two proportion z-test to see, is this different from this? And is this different from that? You could do this one if you wanted, but probably not worth it. Well, I suppose it's pretty easy to run the tests on a calculator. You just kind of run them. You do two proportion z-tests with stats. So just run them all. If you're actually doing the study, you spent weeks collecting the data. Running these tests would take an extra 10 minutes. Putting it in your report, an extra 20. You're like, oh, 30 minutes to be more thorough? Yeah, do it. On a, they're not going to make you do all of those on a exam, IB exam, which is timed. That makes sense. But if this were your IA, yeah, I would do all of them. That makes sense. Because, or if you're doing a college study, if you've spent months collecting data and hours writing, what's an extra 30 minutes to be really thorough and show everything? Or in the case of adding the last one, probably an extra 2 minutes. So, a couple more examples here. Association independence. In the study of heart disease in male federal employees, researchers classified 356 volunteer subjects into their socioeconomic class and their smoking habits. Okay? So, socioeconomic class would be high class, would be wealthy, middle class, lower class. And we've got a total in each of these. However, they made this, they had a lot of high class apparently. And their smoking habits versus current versus former versus never smoked. Okay. Former would be somebody that successfully quit. And we want to know, is there any association essentially between socioeconomic class and smoking? So H naught, there is no association between socioeconomic class and smoking habits. A lot of these are going to be words. HA, there is an association. So computing the conditional distributions. This is probably more useful when I'm looking at it going, is there a difference? What are they doing? They did percentage of high class that are current smokers, former, and never. Percentage of middle class that are current, former, never. Percentage of lower class that are current, former, never. Okay, so they did high out of the total for high. Does that make sense? So this was our current out of total for high, former out of total for high, etc. Those are useful because now I can look and go, yeah, maybe there is, because there was such a different number of totals in there, the numerical wasn't great. The chi-square test, though, will want the numerical data entered. Okay? But if I'm trying to interpret, so here's kind of my graphs of the three. High socioeconomic. Like, there might be a difference. This might be just random variation because the sample size is not that huge. So, computing the expected. Row total times column total over table total. Right? I do not. this is how I would do it. I do not know what they're trying to show above, but row total, column total, that's this one right here. And you need that marginal distribution that we had. Way back here. So here's where they got that number, 211. Row total times column total divided by table total. That makes sense. What's my degrees of freedom going to be on this one? You can't count the totals rows. 4. Okay, do not count the margins in your totals. And so after calculating all the expecteds, I know row total, column total, minus table total. So I can know, what am I looking? There's no association. There is an association, H not HA. My conditions for the test. I'm willing to treat these like SRSs, even though it was volunteers. Because they're not volunteering for any studies, they're just volunteering their information about smoking.
Did people ever get it where it's like they set all this up, but then we just have to answer, no, we can't do this, go through the SRS?
You will always say we will proceed with caution. That's the AP word, but I'm pretty sure we're going, this isn't an SRS, so the results might not be accurate. But if you're the statistician, you're doing the calculations for them anyways. Unless it's totally so bad that you're like, you probably are going to do the calculations, but you're going to tell them that you can't justify using this. But here's what it comes out to. You can't draw your conclusions from it. So let's do this on the calculator. So we got to go back to our original. You do not need to enter any of the totals in your matrix. This is a 3x3. I don't remember the numbers. 43, 92. I think 28. That's a very wrong number. That's going to throw things off. $68, 22. And keep in mind that when this data was collected, smoking was a lot more common. So I've got my data in my matrix. Let's just do stats. So, yep, there's an association. P-value super low. I want to see what happens when I type this out. So it stores my expected matrix in this thing called expected matrix, but I can't get it to, I'm trying to see if I can get it to print it out for me. I'll have to look up how to do that. But it should be able to print it out. So we would have to check our expected matrix, and the book, gives it to us. So does this meet my conditions? Yes, all the values are greater than 5. Was it an SRS? No. So we would have to consider that maybe we can't generalize this. But it's a pretty low p-value, so it's pretty likely that it would generalize. And what's our conclusion? There's an association. We're not telling where the association is, though. But there is a difference between the socioeconomic classes. And it might only be a difference between one of the three. It might not, there might be a difference between middle and low, or high and low, or high and middle, but we don't have the information from this test to give that. So there's strong evidence that smoking, that there's an association between smoking and socioeconomic study of male federal employees. Notice that they're not generalizing this to Americans or males even. Okay. The size and they are described by the table and the display of these percentages. So you can distinguish the types of chi-square tests for two-way tables by examining the design of the study. In an association independence, there's a single sample from a single population. The individuals in the sample are classified according to categorical variables. The test for homogeneity of a population, there's a sample from each of 2 or more populations. So this one was one population, but a different characteristic about them. The socioeconomic status or different characteristics than smoking, but one population, male federal employees. The cocaine treatment was different populations, cocaine addicts trying to quit, taking a different drug and looking at the same thing about them. That makes sense? You were looking at the success rate for them. Abby, are you awake? Are you sure? Does that make some sense? That's your lesson.